Okay, so for problem number 8, we're dealing here with a family of sets that are indexed by this set delta here. And we have that delta is not empty, right? And B is just some set. So we're trying to either prove or these statements or provide a counterexample to them. So for item A, I'm going to say let B be the set 0, 1, and let each A sub A be defined by just their index, right? Where A belongs to delta. And I'm going to say let delta be the set containing 1, 2. So we're saying, hey, script A is a family where each set contains a single element and it contains just the index, right? So what that means is that script A is going to have just A sub 1 and A sub 2, where A sub 1 is just going to have the set, it's just going to be the set containing 1, and A sub 2 is just going to be the set containing 2, and that's it. So now let's check whether this is a counterexample, right? So first let's find the intersection. So the intersection of this family, well, the intersection is just going to be empty, right? Because we can see that A sub 1 has the element 1 and A sub 2 has the element 2, and they have nothing in common. So this intersection is going to be empty. Thus, if I do B minus the intersection, it's basically saying, hey, take the set B and remove from it the empty set. So that's just going to be B, right? Nothing was removed. So that's just going to be the set 0, 1, because remember that B, I said that this was B. So if I go B minus the intersection, which is the empty set, I'm just going to have B itself. Nothing changes, right? And now let's do the intersection of let's do the intersection of B minus A sub A. So if we do the intersection, let's first find B minus A1, and B minus A1 is going to be the set 0, 1 minus the set containing 1, so that's just going to be the set containing 0, and B minus A sub 2 is going to be the set 0, 1 minus the element 2. Well, the element 2 is not in B anyway, so that's just going to be the set 0, 1, right? So if we do this intersection, so maybe I'm going to bring this down here. So if we do this intersection, we can clearly see that B minus A1 and B minus A2, they have one thing in common, right? They have the element 0. So already we can see that these are not the same, because B minus the intersection of the family is going to be the set 0, 1, whereas the intersection of B minus each element in the family is going to be the element containing 0. So that is a counterexample for item A. So let's do item B, and item B is going to be it's going to be similar. Actually, I should not have erased that because I want to reuse some of my notation. So I'm just gonna change the set B. So it's gonna be the set 1, 2, and this is item B. All right. So we're saying, hey, let B be the set 1, 2, and we're saying let each A belonging to the family just contain their index, right? So this means that A1 is going to have the element 1, which is its index here, and A2 is going to have the element 2. And the family A is going to contain A1 and A2. Okay, so from this, let's see if this is a counterexample, right? So B, actually, before we do this, let's find the union. So the union of this family is going to be the set containing all the elements that are in either of the sets. So we're going to join the elements that are in A1 and A2, So the union is going to have the element 1 and 2 because those are in A1 and A2. So if we do B minus the union, well, I'm going to begin with my set B, 1, 2, and I'm going to remove from it the elements that are in the union. Well, all the elements that are in B are in the union, right? So if I remove them, I'm just going to have the empty set. It's going to be nothing in it, right? So we've found one side of the equation here, and now let's find the other side. So if we do the union of, we're trying to do the union of B minus each index. So let's first do B minus A1. And B minus A1, we're going to begin with the set 1, 2, and we're going to remove this element from it. So let me erase this. So if I begin with the set 1, 2, and I remove the element 1 from it, so that's just going to be, it's just going to have 2 in it. And if I do B minus A2, I'm going to begin with the set 1, 2, and I'm going to remove the element 2 from it. So I'm just going to have the element 1 left over. So if I do the union of A belonging to delta, the union of B minus A sub A, so it's like I want to join, let me remove this. I want to do the union, so I want to join B minus A1 with B minus A2. So if I do this union here, I can see that I'm going to have the element 1 and 2. So we can see that these are clearly not the same, right? Because one of them is the empty set, while the other has the elements 1 and 2. So let me zoom out so you guys can see. So this is a counterexample to the claim that these two things here are equal. Okay, so for item C, we are going to show that these are equal, and we're going to do it using a chain of if and only if statements. So we're going to take some element that is here and show that it must also be there, but because we're doing if and only if statements, that also means that we can begin at the conclusion and then work backwards, and so it means that they are equal. So we're going to say we have that x belongs to the expression on the left, so x belongs to the intersection of A belonging to delta minus B. So what we're going to do here is we're just going to unwrap the meaning of this one set minus another, and we're also going to unwrap the intersection. So if this is true, if and only if x belongs to the intersection and A sub A, and x does not belong to B, because if x is in the intersection minus B, it means that it's in the intersection and not in B. So now what we're going to do here is we're going to unwrap this x belonging to the intersection. So we're going to say if and only if, and I'm just going to put a parenthesis here to show that I'm unwrapping this intersection. If and only if, we're going to say for all A belonging to delta, x belongs to A sub A. So we're saying, hey, x belongs to every single set in that family, and x does not belong to B. So now what we're going to do here is just rewrite this, but we're going to move the parenthesis around, and we're going to see that it essentially means the same thing. So if and only if, for all A belonging to delta, it is the case that x belongs to A sub A and x does not belong to B. Right? So it's the same meaning, but all we've done here is we've moved the brackets, because now we can see that, hey, if and only if for all A belongs to delta, if x belongs to each set and x does not belong to B, it means that x belongs to A sub A minus B, right? So all we did here was we joined this x belongs to A sub A and x does not belong to B. And so we're saying, hey, for all indexes, X belongs to the set containing that index minus B. So this here is the definition if and only if X belongs to the intersection of A sub A minus B. So we took some element that was here and we worked it to show that it's here, but because we used if and only if, it means that we can also begin backwards and reason through all these steps and end up here. So we ended up showing a double inclusion, right? And for item D, it's pretty much the same. We're only going to switch the intersection for the union. So I'm going to keep some of these things here. So I'm going to change this to D. And I'm going to change this intersection for the union. All right. So what I'm doing here is taking some element that is here, and I'm going to show that it must be there and vice versa. So if X belongs to the union of this family minus the set B, if and only if X belongs to the union and X does not belong to B. So now we're going to unwrap this union. So we're going to say if and only if. And we're going to unwrap this union by putting a parenthesis. Now the difference between the union and the intersection, we're saying if and only if for some, so not for all, for some A belonging to delta, X belongs to A sub A, and X does not belong to B. So now all I'm going to do here, I'm going to rewrite this, but I'm going to move the parenthesis around. So I'm going to say if and only if for some A belonging to delta, it is the case that X belongs to A sub A and X does not belong to B, right? And so I'm going to move this parenthesis here. And now we're going to join the stuff that is in the parenthesis. So we're saying if and only if for some A belonging to delta, X belongs to, well, if it belongs to A sub A and it does not belong to B, it means that it belongs to A sub A minus B. And now this here, we have created the definition for the union, right? So because this is the definition for the union, we can now say if and only if X belongs to the union of all these A sub A minus B. And so that is it for item D. We, similar to the last problem, we began with some element here and showed that it is here, but because these are if and only if statements, we can reason backwards. So we have shown a double inclusion, and therefore these are the same.